Thank you very much for the introduction. First of all, let me thank the organizers for giving me the opportunity to present this talk, which is based on joint work with Jiří Otrata and Jan Waldman from the Czech Academy of Sciences. Okay, here you can see an outline of the talk. After some short introduction, we will give a review of variational geometry and generalized differentiation. Then become the basic definitions of the semi-smoothness star property. Then we will develop a semi-smooth star Newton method, and I hope I have enough time to present some numerical experiments. Okay, let's start with the introduction. What do we want to solve? We want to solve an inclusion of the form 0 should belong to f of x, where f from Rn to Rn is a set-valued mapping. Okay, of course, this is a very general problem and a very fundamental problem in mathematics. Let us first consider here a special case, namely that we want to solve equations. Well, that is that f is single-valued. And let us recall now the semi-smooth Newton method for equations. Okay, let us assume that our mapping f is Lipschitzian. And then the semi-smooth Newton method consists of the following procedure. Given some iterate xk, let us choose some matrix ak belonging to the generalized Jacobian of f at the point xk, and compute xk plus 1 as solution of this linear system f of xk plus ak times x minus xk equal to 0. Here below you can see the definition of the generalized Jacobian, which is nothing else than the convex hull of the so-called B subdifferential of the mapping f. Okay, what do we know about convergence of this semi-smooth Newton method? We need two types of assumption. The first one is some smoothness assumption, and the second one is some regularity assumption. Okay, how does the smoothness assumption looks like? That means that for all points x close to x bar, to a solution x bar, and for all matrices A belonging to the generalized Jacobian of f at the point x, we have this estimate here. So f of x bar minus f of x minus a times x bar minus x behaves like little o of norm of x minus x bar. Okay, that means that our linearization is accurate enough to ensure convergence. Yeah, and the second one is a regularity assumption. For instance, that all matrices A belonging to this generalized Jacobian are non-singular. The smoothness assumption here is in particular satisfied if the mapping F is semi-smooth. You see here the definition of Key and Sun of semi-smooth functions. Okay, it says that for all directions u here, this limit exists. One can give an equivalent characterization of the semi-smooth star property, namely here that this smoothness assumption is fulfilled and the mapping F is directional differentiable. Semi-smoothness goes back to Mifflin. It's a very old property. And okay. So now let's come to variational geometry and generalized differentiation. First of all, let us recall some basic definitions from variational geometry. Here you see the definition of the tangent cone. The regular normal cone is defined as the polar cone of the tangent cone. Then you have here the limiting normal cone, which is given by elements u star, which are the limit of regular normals at points xk converging to the point x bar under consideration. Okay, and if we restrict here this limiting procedure to some directional limit, then we obtain the so-called directional limiting normal cone to the set A. Having these definitions from geometry, we can define generalized derivatives. Okay, first of all, we consider here the graphical derivative. The definition is as follows: the graph of this graphical derivative, which is a set-valued mapping, is nothing else than the tangent cone to the graph of our mapping F under consideration. And also the regular coderivative and the limiting coderivative are set values mappings. Okay, the graph of the regular coderivative is defined via the regular normal cone to the graph of F. Not directly, you have here to interchange the arguments and also to introduce here a minus sign, but essentially given here by the regular normal cone to the graph of F. And the limiting coderivative is analogously given by the limiting normal cone to the graph of F. And finally, we can introduce also the directional limiting coderivative of the mapping F via the directional normal cone to the graph of F. Sorry, my coffee machine is switching off now when you hear the noise. Okay, what do we know for single-valued mappings? If F is continuously differentiable, then the graphical derivative coincides with the usual derivative of F, and the regular and the limiting coderivative coincides with the point of the Fréchet derivative of our mapping F. Okay, and what happens if F is Lipschitzian near X bar? Then we know that the B subdifferential and the generalized Jacobian are related with the limiting coderivative of F, not related with the graphical derivative, with the coderivative. This will be important later. Okay, now how can we use these generalized derivatives to linearize our set-valued mapping F? Okay, consider for instance in the Josephi-Newton method, where you can split the mapping F into a single value part and a set-valued part. Okay, then you make only a linearization of the single value part. The set-valued part is now linearized. Okay, and there also exist some Newton methods based on the graphical derivatives, which you can see some reference here below. We want to use a different approach. This is now introduced in the next section. We call a set A semismooth star at the point X bar in A. If for all directions U, the following relation holds that all directional limiting normals in direction U are orthogonal to the direction U. So that the scalar product of X star and U is 0. Okay, and the definition for set-valued mappings F is they are semismooth if the graph is semismooth at the point belonging to its graph. Okay, we have the relation between the coderivative of F and the normal cone to the graph of F. So we can here write this definition also in terms of elements of the directional limiting coderivative. Yeah, some remark, where comes this definitions from? 2 years ago, we made a paper together with Asen Donchev and Alex Kruger and Jerzy Otroda about the radius of matrix subregularity. Okay, and there was considered a stability of matrix subregularity under semismooth perturbations. And in this formula for this radius of matrix subregularity, exactly this condition here appeared. At the first moment, I did not know how to use it. Yes, and then we had the idea to use it for the definition for this semismooth star property. Yeah, this definition is in some sense elegant, but maybe it is not the easiest one to imagine what a semismooth starness means. So let us consider equivalent definitions. For instance, here, the second point here, consider a point x, which is close to x bar, and consider a regular normal x star at the point x, and then consider here this quantity. This is nothing else than the cosine between the normal x star and here this direction x minus x bar. Yeah, and this cosine should be less equal epsilon. So these normals should be nearly orthogonal to this direction x minus x bar. And the similar relation holds not only for the regular normals, but also for the limiting normals. Okay, now yeah, we can illustrate here semismooth sets. Consider here a point x bar, then here a point x, consider here a normal x star, and so that means that this normal x star is approximately normal to this direction here, x minus x bar. And you can show at every point that this holds true. Yeah, what do we know when sets semismoothness star? Okay, only two cases here. Every convex set is semismooth star at each point of its set, and the union of finitely many semismooth star sets is again semismooth star. So on base of this, we could also say immediately that this heart is semismooth star because it is the union of two convex sets here. Okay, this implies, of course, that every closed convex multifunction is semismooth star, or polyhedral multifunctions are semismooth star. And further also, the sum of a smooth mapping and a semismooth star mapping is again semismooth star. Yeah, what is the relation with the semismooth property? Yeah, consider the case that the mapping F is single valued and Lipschitzian. Then if F is semismooth, in the sense of key and sum, then it is also semismooth star. And conversely, if F is directional differentiable and semismooth star, it is also semismooth. So that means that semismooth star is a little bit weaker than semismoothness for Lipschitzian mappings, but it is also a little bit more general, yeah, because a semismooth star property is also defined for non-Lipschitzian mappings. And there exists an other characterization of semismooth star property. A set A is semismooth star at the point x bar if and only if the distance function is a semismooth star at x bar. So having these concepts of semismooth star property, let us introduce now the semismooth Newton method. Yeah, consider again here this inclusion that we want to find some point x bar such that 0 belongs to f of x bar. And let us consider some iterate xk which is close to x bar. Yeah, and now we have to consider the case that we are dealing with set-valued mappings. It does not mean that f of xk is not empty. Well, it could easily be that f of xk is empty. Or we can also not assume that 0 is close to f of xk. That is, in the first step, we have to compute an element, let's say x hat k and y hat k, belonging to the graph of f, which is close in some sense to xk and 0. Okay, and we call this step here the approximation step. And now let us come to the Newton step. By the definition of the semismoothness star property, we know that for every y star and x star belonging here to the graph of this co-derivative of f at x hat k and y hat k, this relation here holds. Well, you have here x star x hat k minus the solution x bar is y star y hat k plus some little o term here. Okay, and if we neglect here this little o term, we have one equation for this difference x hat k minus x bar, which we want to compute. Yeah, one equation in Rn. Okay, let's repeat this procedure. Let's choose n elements belonging to the graph of this co-derivative. Let's call them y r star and x I star, and then we have a system of n equations, defining our Newton step. Well, we choose the next iterate xk plus 1 as the solution of this system here. Let us formalize this procedure. We introduce now for a given point xy, this set AF xy as the collection of all matrices A and B, such that the rows of A and B are given by elements yr star and xi star belonging to the graph of the co-derivative of f. Yeah, and we want to solve a system of linear equations that we require that also the matrix A should be non-singular. This yields the definition of this set A reg f at the point x and y. And then the Newton step can be written in the following form. Xk plus 1 is x hat k minus a minus 1 b y hat k. Yeah, what do we know about the accuracy of this Newton step? Yeah, if we have our point x hat, y hat close to x bar or 0, then for every pair A and B belong to that A reg f x hat y hat, we have this estimate here. This is the outcome of our Newton iterate minus solution is less equal some small quantity. And now here term depending on our chosen matrices A and B. Yeah, times here the difference from our approximation step here. So that our Newton procedure works, yeah, we also have to guarantee that this quantity here remains bounded. Yeah, when does something like this exist? Recall the definition of strong metric regularity. A mapping F is strongly metrically regular if the inverse mapping has a single valued Lipschitz continuous localization with Lipschitz constant, let's say, kappa. Yeah, and now assume that F is strongly metrically regular around some point x hat, y hat with modulus kappa. Then there exists some matrix C with norm less equal kappa, such that the identity matrix and C belong to the set A reg of F. Yeah, okay, and so that means that the quantity which we had before here, a minus 1, this is the identity, and this term here is also bounded. Yeah, we have guaranteed this. Okay, this is the following outline of the semi-smooth Newton method for solving inclusions. Choose a starting point x0, set the iteration counter k equal to 0. Okay, if the point xk is a solution, stop the algorithm. Otherwise, perform the approximation step here, and then select matrices A and B belonging to a reg of F, and compute the new iterate xk plus 1 as x hat k minus the inverse of A times B times y hat k. Increase the iteration counter and go back here to step 2. Okay, this is not really an algorithm. You have to consider it as a roadmap for solving such inclusions. Of course, you have to fill in here this approximation step and how to choose this matrices A, B for a real problem. Okay. Yeah, what do we know about convergence? Okay, let us introduce here the set G, which depends not only on our mapping F and the solution X bar, but also on some constants L and kappa. Yeah, this is the set of all points X hat, Y hat, and A and B, which satisfy the following properties: that X hat minus X bar and Y hat is less equal the constant L times X minus X bar. Okay, and A and B belong to the set A reg of F, such that this quantity here is bounded by kappa. Okay, this set G of X means these are the points X hat and Y hat, which we have to choose in our approximation step. Yeah, and these are the matrices A and B, which we have to choose in our Newton step. Yeah, and note that this condition here for the approximation step is in particular fulfilled if we choose our point X hat and Y hat satisfying this condition here. That is, we have only to choose some approximate projection of the point X and 0 to the graph of our mapping F. Okay, and now let us assume that our mapping F is semismooth star at x bar 0, and we assume that there are constants L and kappa, such that for every x, which is not the solution of our problem, which is close to x bar, we have that this set G L kappa F of x bar and x is not equal 0. Then we have locally superlinear convergence of our algorithm, provided we choose in every iteration here x hat k and y hat k and a b to this set G L kappa of xk. Okay, and now of course the question appears: when is this condition here fulfilled, that the set G L kappa of x is not empty? This is answer gives us the following theorem. Let us assume that F is semismooth star and strongly metrically regular around the solution. Then the assumptions from the previous theorem are fulfilled. That is, we can achieve superlinear convergence. Okay, and now let us mention that a strong metric regularity is not a necessary condition for convergence. Yeah, let us come to some numerical experiments, and let us also demonstrate how to implement the approximation step and the Newton step. Let us consider the following variation inequality of the second kind. We want to solve the inclusions here should belong to f of x, which is given by the sum of a smooth mapping f plus the subdifferential of a proper convex and lower semi-continuous function q. Okay, we do not apply the semismooth Newton method. We apply some splitting. Yeah, we introduce an auxiliary variable d, and then we want to solve here this inclusion here. 0, 0 belongs to f of x and d. This is f of x plus the subdifferential of q at the point d, and here x minus d in the second component. That means that x should be equal to d. Yeah, due to this special structure, the auxiliary variable d can be eliminated afterwards. Okay, let us consider the case that we are given some iterate xk. How can we perform the approximation step? Yeah, we can use, for instance, the forward-backward splitting method for performing here this approximation step. That means let's choose gamma k, well, for instance, equal to the norm of the Jacobian of f at the point xk plus some small constant. Yeah, and compute uk as a unique solution of this problem. And then we set x hat k equal to xk and d hat k equal to xk plus this uk. So, and you can see here with this formula that this d hat k is exactly the outcome of one forward-backward splitting method. Yeah, how does the Newton step looks like? Yeah, here we use here the following result. We have to compute the co-derivative of the subdifferential mapping. Yeah, and we are interested in particular in subspaces of dimension n contained in the graph of the co-derivative of the subdifferential mapping. Yeah, and there exists a following result. There exists always a semi-definite, positive semi-definite and symmetric matrix G having norm of G less equal 1, such that the range of identity minus G and G, that this subspace is contained here in this graph of the co-derivative of the subdifferential mapping. Now, and using such a matrix GK, yeah, we can write down our Newton step in the following form: GK plus identity minus GK times Jacobian of f at xk times s equals to this expression here. Solve the system with respect to s and set the new iterate xk plus 1 to xk plus sk. Yeah, and as a stopping criterion, we will use that our residual, that is the outcome of the forward-backward stepping, is less some given tolerance epsilon. That is the following theorem. We assume here that this subdifferential mapping is semismooth star at the solution. Then we obtain local convergence under the assumption that the mapping F is metrically regular around the solution. We need not strong metric regularity, we only need metric regularity. And it's to say that also some globalization is possible. When F is monotone, we can globalize here this semismooth star Newton method. We can prove convergence by using some line search. Okay, and when F is not monotone, we use some non-monotone line search heuristic. Okay, and then we perform here actual some computations. First, we compute a randomly generated matrix C with elements in -1 and 1. Then we compute here this matrix A by C transpose C divided by N. This is symmetric and positive definite with probability 1. And then we have also here this skew symmetric matrix C minus C transposed, and then set f of x equal to beta times x transposed ax times ax plus sx. Okay, So this means here, this defines here some strong monotone part here. Yeah, and if we decrease this beta, we can decrease also this constant of strong monotonicity. And also here the function Q is computed in some random way. First of all, we assume here a separable structure in the following form. And here this component functions Qi, yeah, are piecewise quadratic functions. You see here a picture for the graph of the subdifferential of these mappings Qi. Here, this depends also on some chosen parameter tau here, which we choose here.
Excuse me, Helmut. Yeah. Could you please wrap it up? We have enough. Thank you.
Okay. Now you see here our results for the case when F is monotone. Yeah, you see here the results from the Newton method. This is here this line in magenta, compared here with the forward-backward splitting method and Douglas-Reckford splitting method for different dimensions n. Here n equal to 150 and here n to 2400. So, okay, if we choose beta and tau equal to 1, yeah, so also the forward-backward splitting method and Douglas-Reckford are able to compute a solution with relative high accuracy. If we decrease this constants beta and tau, yes, so they does not give us a solution. Whereas here you can see that the semismooth Newton method works very well. Yeah, okay, and now let me present the last slide. So these are the results for the Wombat challenge for the problem posed by Claudia yesterday, where you have here to consider the minimum of this function f of x here. Yeah, here let us split this. Okay, in the interval of -1000 to +1000, we have here on a grid of 40,000 grid points. Yeah, we have considered here the iteration numbers for all the starting points, and you see here for every starting point here we need 2 iterations of our semismooth Newton method to solve the problem. The only exception is when we start here at 0, then we need 0 iterations because we are at the solution. Okay, this is all. Thank you very much for your attention.
Thank you very much. Any questions and comments for Helmut Gfrerer?
Yeah, I have one. Abderrahim from France.
Okay, please
from France,
go ahead.
Yeah. Yes. Yeah. Hello, Helmut.
Yeah.
Yeah. Many thanks for your talk. I have 2 questions. The first one concerns the use of metric regularity for studying a Newton method.
Yeah.
Namely, the set valid map in F plus the subdifferential of Q.
Yeah.
How to get metric regularity for this set valid mapping? This is my first question. The second question, do we need really metric regularity to study the Newton method? Or I think calmness is enough now.
If you have, okay, if you have only that means metric subregularity, that means strong metric subregularity, you will need something like this. You will need that the solution is an isolated solution. You cannot expect that the Newton solution converges to some point which is not isolated, yeah? Or this converges fast to this point, yeah? Okay, then you also need the solvability of the subproblems. And if you only have metric subregularity, then the solvability of the subproblems is not guaranteed. This is a point where metric regularity comes into play. Yeah, if you have another condition which ensures the smoothability of your subproblems, yeah, okay.
Okay.
Okay, sorry, I'm sorry, we have to stop here. Could you please continue with the questions offline?
Okay.
Thank you very much